Hey there everybody, welcome to the final video in our SIR model unit. In this video I want to show you some models that are not classical SIR models, but they are built on the same type of logic that those models were built on. And the reason I want to show you this is that if you go to a search engine like Google Scholar and type in SIR models as a search parameter, you will get thousands upon thousands of hits. And some of those hits are the classical SIR models. However, the majority of those hits are SIR type models, models that are built on that logic. So I want to give you a taste of what those models are like. And as you can tell from thousands upon thousands of hits, these models are very much alive and well, very much in use. So by way of introduction, if we're going to talk about models that are built on the same type of logic as the SIR models, it's worth revisiting what was the logic upon which we built the SIR models. So here's the general framework of that construction. There's a thing that we were thinking of as the flu or COVID-19. That thing spreads via human-to-human contact. Now it's worth pointing out, the models that we built didn't care that we were talking about the flu necessarily, right? Like the pure math of it didn't care that we were talking about a specific disease. That's what's so nice about the math, right? It can abstract you away from the concrete to give you a general framework, and this was that framework. The population itself can be divided into distinct groups where those groups were defined in relation to the thing that's spreading. Furthermore, there is some sort of flow between the population groups, and that flow is driven by the contact between the groups or by some sort of external factor beyond our control, such as that K parameter in the SIR model. So that K parameter basically said, well, if you have the flu, you're sick for 3 days. So on a given day, a third of the sick population should recover. So in the classical SIR model, the flow from I to R did not depend on any contact between the groups. So basically you have flow, where that flow is either driven by contact between the groups, like S to I flow, right, going from susceptible to sick, or you have flow that's just like, hey, on a given day, a fixed proportion of people flow from one group to another. That was the basic logic of the SIR models. Well, it sure seems like there are many other things out there that might be modeled by the same kind of logic. Maybe not the exact same model, right? Maybe not a classical model, but there are other things that are epidemic-like, and we use the language of epidemic. So think about an opioid epidemic, an obesity epidemic. There are epidemics of, say, terrorist ideas. You can get outbreaks of terrorist ideas on the internet. And I have seen papers that use SIR type models to model the spread of terrorist ideas. That's like a disease on some level, isn't it? So all three of these sorts of things, these are not the flu, okay? These are not COVID-19. If I am an opioid addict, okay, I'm addicted to heroin or something, if I sneeze on you, you do not become a heroin addict yourself. However, how does a heroin outbreak happen? How does an obesity epidemic happen? Things like this, right? Generally speaking, they spread via human-to-human contact, right? If you become addicted to opioids, it is most likely because you came in contact with the group of opioid users. Not always, of course, right? Maybe you came into contact with doctors who prescribed opioids to you, right, in that particular case. But in any case, the same sort of logic that wrote the SIR models could probably be used to build models for anything like these three things. So in this video, I'll show you models dealing with this, opioid usage or heroin usage, and then in the homework, you'll deal with obesity models. Okay, so let's start with the first heroin epidemic model due to Comiskey-White in 2007. So back in 2007, people hadn't quite become comfortable with the language of opioid epidemics. However, people had noticed an uptick in heroin usage. So we hadn't quite noticed that we were in the midst of an opioid epidemic the way we know that now, right? So this paper was, as far as I'm aware, the first SIR type paper to address an uptick in heroin usage. And just like with the SIR model, if you're going to start building a model for something like that, the first thing you do is define your population groups and build a flow diagram. In the SIR models, the flow diagram is very simple. S flows to I, flows to R, like that. This model here has 4 population groups, and the flows are more complicated. But this is how you always start. Define your populations, and then define your flows, like who can flow where. So they have 4 groups. Susceptibles, these are people who have not used the drug but might use the drug. Heroin users who are not in treatment, that's group U1. Heroin users who are currently undergoing treatment, that's U2. And recovereds, where being recovered in this case means that either you have died, which was the case in the classical SIR models, either you've died or you are no longer susceptible to heroin usage. And these are the various flows. And by the way, Comiskey and White assume that regardless of which population you're in up here, you can become recovered by deciding not to use heroin anymore. So if you're susceptible, you can just declare, I will never use heroin, and you'll move into this group. If you're a heroin user right now and you stop using and declare you will never use again, you flow this way. So anyway, there are their population groups and there are their flows. Once you have that flow diagram, how do you build a system of DEs for those variables? Like how do we do that back with the SIR model? Well, it all depends on the assumptions you're making about like levels of contact and like how the flows work. Do you just have a fixed proportion of people flowing from one group to another? Or does the flow depend on the amount of contact? Also, how long-term is the model? So do you want to include like a natural death rate of the population as people are dying from cancer over the years? Things like this. So just to start thinking about that, let's answer this question here. What controls the flow from susceptible to drug user? Presumably, that flow is driven by contact, human-to-human contact between susceptibles and drug users. So again, specifically when you're talking about heroin, I am not aware of any case where somebody became addicted to heroin because they found a needle on the ground or something and started using, right? So generally speaking, you have to have come into contact with people who are already using heroin to become a heroin user. Again, with other contexts like general opioid usage, that's not the case. You can be prescribed an opiate by your doctor, right? That doesn't require any human-to-human contact between a non-user and a user. But in this particular context of heroin, that's what we're assuming. So anyway, what controls the flow would be like the amount of contact between the two groups and the likelihood that a given contact between a susceptible and, if you will, an infected produces a new infective. So there's just like an effective contact rate that I'm going to call beta 1, similar to that effective contact rate parameter B from the SIR models. So just like in the SIR models, on a given day, each drug user who's not in treatment is going to generate this amount of new drug users per day from the susceptible group. So here's my effective contact rate, this beta 1, and then capital S over N. N is still the total population, just like before. S over N is just the proportion of susceptibles in the population. So this was just like with the SIR model, except I've replaced a B with the beta 1 for this new context. And then just like in the SIR model, if each infected generates this many new infecteds on a given day, then the total number of new infecteds, the total number of new drug users on a given day is given by this quantity here. Right, just multiply by the total number of infecteds. Okay, well, we'll assume that the flow from U2 to U1 occurs in the same fashion. So U2, these are heroin users currently undergoing treatment. So we'll assume that relapse occurs because of bad influences from their friends or something, right? That if you're in treatment, you perhaps have friends who are still using who might pull you out of treatment. So we'll assume some sort of effective contact rate beta 2 for that, driving that flow, and so on. So basically for every one of these arrows, you can decide what is driving that flow. So let me just show you now a system of DEs. There are 4 people groups. I left off the differential equation for R just for the sake of time. But just like with the SIR models, or sorry, not for the sake of time, for the sake of space. Anyway, just like with the SIR models, your derivative is your rate in minus your rate out. So with S, there are 2 arrows out and no arrows in. Therefore, it's all negative terms in here, modeling outflow. So this quantity right here that was the number of people leaving the susceptible group to become drug users on a given day. So that's outflow becomes negative and then becomes inflow for the drug user group. This term here, this is flow from S to R. So mu1 here in their model is defined as the removal rate of susceptibles from the system to become recovered. So that mu1 parameter includes like a natural death rate of the population. If you are susceptible, you can still die of cancer or something, right? Plus the people who recover by deciding not to take the drug. So mu1 is just kind of a general rate of flow from S to R. The authors assume that that flow is not driven by contact between groups. This is more like the K parameter from the SIR model. It's just on a given day, some fixed proportion of susceptibles recover either by dying or by deciding not to take the drug. Okay, let's look at the U1 prime DE here. We've already talked about this term. There's a similar term here. Notice a beta 1 replaced by beta 2 and an S replaced by a U2 because this is flow from U2 to U1. So it's like a relapse arrow here. By the way, let me note real quick that sometimes in these models, this beta 1 over N is just written as a beta 1. So they take this parameter here and just include the division by N in this number, just so you don't have to write these clunky over N's every time. So just be aware of that. You might see that sometimes. Okay, so that explains this term and this term. These sort of terms exist when the flow is driven by contact between groups. This term here, notice, there's no mixture of groups. It's not U1 times something. This is just taking away some fixed proportion of U1. So Comiskey and White assume that on a given day, there's just some fixed proportion of drug users who enter treatment, and tau just is that fixed proportion. So in other words, they're assuming this arrow here isn't really driven by contact between any particular two groups. They're just assuming that like today, 1% of users enter treatment. That's the same today as it is the next day and so on and so on. So this tau is behaving more like a K parameter as opposed to this beta 1, which is acting more like a B parameter, a contact rate. So anyway, in these models, you just have a bunch of different parameters. Some of them are acting like B parameters, some like K. It all depends on the assumptions you're making, basically. Finally, in this U1 prime equation, notice here they have minus, and this is a constant parameter, times U1. So some other fixed proportion of U1 is also leaving the U1 group. This flow here, though, this outflow is this bottom arrow flowing to recovereds. So this mu2 parameter is the removal rate of drug users from the system. This includes the natural death rate from the population. So if you are a heroin user, you can still die from other causes not related to heroin, right? You can die from cancer, whatever. So that's included in mu2. Also, as I said up front, they assume that at any time, somebody can like stop using, declare they will never use again, and then they will count as recovered. So mu2 also includes that. So it's just like a general removal rate from mu1. Now, if you are a drug user, there's some sort of like enhanced death rate for that group. That group, you just are more likely to die. So delta 1 is like the enhanced death rate for that group. So you take sort of like a general removal rate from the population and enhance it a little bit. Okay, so all that to say, right? U1 has 4 arrows. 2 going out, 2 coming in. So there are 4 terms here. Each of those arrows has a term. Now, by the way, you might have more terms here for the following reason. So something like, let's think, something like this incoming flow here, right? This outgoing flow from here to here, U1 to U2. Comiskey and White just assume that there is some fixed proportion that enter treatment on a given day, and they don't assume that's driven by contact between the groups. However, it is possible, and you might want to include this, that some fixed proportion does just decide, without any interaction, I'm going to enter treatment today. However, there may also be other users that are influenced by people in treatment to go to treatment. So there might be actually kind of like 2 arrows, if you like, from U1 to U2. One arrow is just a fixed proportion arrow. The other arrow could be driven by contact. So you can modify the model however you want. Okay, so in conclusion here on this model, if you want to build a system of DEs like this, you build a flow diagram, decide how the flows go. Every flow, generally speaking, comes with a parameter on it, and you have to define them. You have to say what they are. So if you look at the Comiskey white paper, you'll see all these things defined. Then you build your system of DEs like this. So the more flow there is, the more stuff there is, right? And if you want to use this model, there's a lot of sort of empirical work you have to do. You have to start estimating all these parameters if you want your model to be accurate. Okay, so before leaving this model and sort of quickly wrapping up by looking at some other ones, let me just point out that, or just ask, why would you do this? Why are Comiskey and White doing this? Let me just show you the abstract of their paper somewhere here. Here's the abstract from their paper. I'm not going to read all this, but it says, blah, blah, blah. The aim of this model is to identify parameters of interest, etc. And then look at this. With a view to informing and assisting policymakers in targeting prevention and treatment resources for maximum effectiveness. That's why they're building this model, to assist policymakers in this way. And then notice how they end their abstract. They say this. A key result arising from this model is that prevention is indeed better than cure. Okay, so they build this model so they can make predictions so that hopefully, as epidemiologists, they can help policymakers. They can build a better society and help us understand how to treat a heroin epidemic. Okay, so I want to show you two more models in this video. I don't want to show them, I don't want to go through all the details because that takes a while like this, but they're built in the similar fashion. Flow diagram, DEs, parameter list like this. Okay, so let's move on to a second heroin epidemic model. This Comiskey-White model, there are many criticisms you might have of it. Here are 3 of them. So criticism 1 might be something like this. So we're saying that like if a drug user just stops using the drug and declares they're recovered, then they are, and they get immunity the same way you get immunity from the flu. Right? Is that true? Probably not, right? So shouldn't there be like an arrow, maybe like this arrow here, right? Shouldn't there be an arrow flowing this way also? You know, like you can become susceptible again after use. Shouldn't there be multiple groups of susceptibles? Maybe a group that has never used before and another group that has used before. So it's like susceptible group 1, susceptible group 2. Does it make sense that all users, like this U1 group, are all sort of in the same group? So it seems like maybe the non-treatment group maybe should consist of like light users, heavy users, medium users. I don't know, right? So there's all sorts of criticisms you could make of this model. Now I should say Comiskey and White are of course aware of these criticisms, right? This is not a surprise to them that they didn't include these. However, what they would say is that any model is an approximation of reality. You're always going to lose something when you build a model. We are trying to build something simple enough to be used. So yeah, you can build a model that addresses all of these things, but that model will be more complicated. And we think our model, simple though it is good enough to help with policymakers. However, you could, of course, if you want to, build a model that takes all these criticisms into account. Let me quickly show you one of them, this one. Okay, so this is a Batista model from 2009, I think. So pretty recently, or pretty soon after White Comiskey. This guy says, to amend the White Comiskey model, so we assume blah, 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 right? We wish to amend their model to incorporate multiple drug user classes. So this guy is just saying, like, look, all those criticisms, I'm going to build a model that takes all of them into account. And here is his flow diagram. So you have susceptibles of class 2. These are people who are coming out of treatment, so they've used before. You have these susceptibles here that have never used before. Notice he has arrows flowing out of the system. These are flowing to like an implied recovered class. He just doesn't include that R box in his diagram. So he basically has 6 groups of people here. Light users, heavy users, 2 classes of susceptibles, and users who are in treatment. So if you have 6 boxes, 6 classes, now you got to build 6 differential equations, all with their own parameters, you know, and here is that. Again, he leaves off the dRdt differential equation, he has 5. So as we scan our eyes over this, notice basically like, look, here's a term like this, mu S1. So the class of S1, let me look at that. There's just some outflow to recovered. So on a given day, some fixed proportion leave the system. So that term is not driven by contact between 2 classes of people here. But notice he also has terms like this. L times U over N times sigma 1. So sigma 1 must be like a contact rate. beta 2, ls2 over n. He also has these decaying exponentials, which I won't go into right now. You don't have to include these if you don't want to. I'm putting this paper on Moodle so you can read his explanation for why these are here. But you don't have to include them. Beta 2 must be like a contact rate, effective contact rate between L and S2. And since this is a plus right here, and this is L prime, that must be inflow. And so on, right? So again, if you scan your eyes over this, this looks a lot like an SIR model with fixed proportions leaving or coming in versus like contacty kind of flow, right, between two groups. So here is Batista's model to model a heroin epidemic or a heroin outbreak. So you yourself, right, could think of more classes of people, or maybe you disagree with his flows. Like he's got flows back and forth. That seems to make sense, right? Flows back and forth. That seems to make sense. And so on. Like you can imagine this susceptible class here. You can imagine jumping straight from there to heavy users, right? He doesn't have that arrow. You could build a model that has that arrow, and so on. So anyway, this is a lot of how math modeling works. There's a model out there. You think you can maybe do better. Batista has a lot of work on his hands. Look at how many parameters there are in this model. He describes them all, right? And then he's going to have to go estimate all those things from the literature. And that seems hard. I mean, maybe you can. Okay, so let me show you one more. Yeah, so here I just say what all the classes are. His model has more groups than Comiskey-White, so that comes at a cost, right? Oh, and in particular, right, a lot of empirical heavy lifting to estimate each of those parameters. Let me now show you an opioid epidemic model. This is from 2018, again from our friend Batista. He has a couple co-authors this time. If you want to model an opioid epidemic, that's a little different from a heroin epidemic. Mainly because many people who are addicted to opioids were prescribed the opioids in the first place, right? So this model has 4 population groups: susceptibles, prescribed users, people who've been prescribed but are not currently addicts. Then you have an addicted group. This addicted group in their model, by the way, includes all people addicted to opioids, whether they were prescribed them or not. You can, of course, become an opioid addict without being prescribed anything. And then people who are in treatment. For reasons I don't understand, they don't have a recovered group, even implied. They assume that anybody who dies flows back into the susceptible group. In their paper, they say they do this to keep the population fixed. Okay, I don't understand why you would do that. Why not just have like a sort of a sink box of R where the dead flow? Or just have a dead group. I don't know. It seems weird to throw the dead back into the susceptible group. Let me just show you their paper real quick. Here's their flow diagram. You can flow from susceptible to being prescribed. You can also flow straight from susceptible to being addicted. So again, you can just become like a heroin user. That counts as being an opioid addict without being prescribed. From prescribed, you can flow to being addicted. And notice, they're just assuming, because they have a term like this, they're just assuming that on a given day, some fixed number of prescribed users become addicts. Here, notice on this arrow from S to A, they have 2 different sort of terms here. They assume that you can go from S to addicted in 2 ways. You can, of course, have contact between S and A. Like you can be in contact with people who are heroin users who were never prescribed. You could also, though, flow from S to A because of contact between S and P. So imagine that like your spouse has been prescribed opioids and then suddenly you start using, right? So there's some sort of contact between S and P that might drive this flow here and so on. You can see what all the flows are. This paper also is on Moodle if you want to dig into all the particular arrows. But again, if you look at his SIR model that he builds off of this, the S dot, the dot is just sort of a more old-timey, more physicsy maybe, notation for S prime. So this is like a dSdt, dpdt, and so on. Again, notice the sort of terms they have. This outflow from S is just a fixed proportion. So there's some fixed proportion of the susceptible population that flows into the prescribed population. That doesn't really depend on contact between S and P. However, there are also terms like this. So this is just a constant times SA. So that's driven by contact between the 2 groups. Again, I don't want to go into the details to save myself time here, but you can read why they decide to separate this constant into 2 pieces like this. But notice, just overall, right, they just have sort of like mixture terms with like effective rates on them, or just fixed proportion terms, just like the classical SIR model. So again, this is on Moodle. You can read it if you want to. Okay, so just to conclude here, if you want to model the spread of a thing through the general population, you can use SIR type logic to build an SIR type model if the following things are true. You can divide the population into distinct groups defined in terms of their relation to that thing that's spreading, be it opioid addiction, heroin addiction, obesity perhaps, as you guys are doing the homework. You can create a flow diagram showing the possible flows between the groups. The flows between the groups, say from group X to group Y, occur either because just some fixed percentage of X flows to Y on a given day or on a given time unit, whatever, regardless of any interaction, in which case you see terms like this. Or because those interactions, or because the flow is determined by interaction between the groups. So you have like a contact rate parameter. And again, sometimes the divided by n, that over n is just incorporated into this constant here. So you can write it either way. So in your homework anyway, when you deal with obesity, we think satisfies these three conditions. So you will build your model, build the DEs, give me the list of parameters and what they mean, and show me your flow diagram. Okay, so this concludes our SIR models unit.